Okay, so welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very fortunate to be joined by John Stillwell, who's come to us from University of San Francisco and Monash University, where he has a teaching appointment. John got his master's at Melbourne University and then did a PhD at MIT in Massachusetts. John is a well-established mathematics writer. He has a number of books that he's written, including Mathematics and Its History, which is in its third edition, Geometry of Surfaces, Elements of Algebra, Numbers and Geometry, Elements of Number Theory, The Four Pillars of Geometry, and a couple that are designed for the more popular audience, Yearning for the Impossible, The Surprising Truths of Mathematics, and Roads to Infinity. Today, John's going to talk to us about an overlap of his interests and those at the SETI Institute, and he's going to talk to us about ET math. How different could it be? So if you'll join me in welcoming John.
Can everybody hear me okay? Oh, well, thank you very much all for coming, and thank you particularly to Adrian for inviting me and organising my visit. ET math, or alien math, is something that has intrigued me for some time, but I've never had the opportunity to speak about it before. So I'm grateful for this opportunity, and it's given me a chance to try and get my thoughts in order to some extent. Now, I realize that many of you will not be mathematicians, so I will try to explain everything from first principles, but no doubt it will get a little far out. But that doesn't matter too much, because one of the points I want to make is that mathematics can take strange forms which are very difficult to recognize, and I think this will pose a problem for SETI in trying to identify mathematical information if it ever comes to us from outer space. So to begin, let me try and establish a kind of point of view about the nature of mathematics. Oops, that's going backwards. There are different views on the nature of mathematics, and some are more parochial than others. And so the most parochial, I think, is to say that math is an artifact of human cultures, and different cultures have different math. And that sort of leaves math in a very small place. It doesn't leave any possibility for extraterrestrial math. So I think most of us would feel that's too restrictive. Another one that's fairly common is that math is an artifact of the human brain, so it's human-wide, but somehow dependent on the structure of our brains. Now, this idea has a lot of merit, because obviously the way we think about math must be influenced by the structure of our brains. But again, it doesn't leave any possibility of mathematics occurring elsewhere in the universe. So I think we have to go further and be more universal than that. And a lot of mathematicians, myself included, believe that math exists whether or not there are beings who can comprehend it. This point of view is called Platonism, after Plato, who had this view. This perhaps is an extreme point of view, but it's a convenient one, because it certainly leaves the possibility of alien or extraterrestrial mathematics very much open. And a nice statement of Platonism was given by the mathematics writer Martin Gardner, and I like this instance of I guess you can read it. If two dinosaurs were to join two other dinosaurs in a clearing, there would be 4 dinosaurs, and whether or not anybody was around to observe it, and whether the dinosaurs were smart enough to know it, it is simply a brute fact of the universe that 2 + 2 = 4. So I hope we can agree on that there are some universal mathematical facts. And so there is the possibility of extraterrestrial mathematics. But that still leaves plenty of problems, because we human mathematicians are accustomed to thinking of mathematics not merely as a collection of facts such as 2 + 2 = 4, but also a way of organizing facts. And we like to organize facts by proving them and establishing some sort of basic assumptions and letting other facts be deduced from them. But then again, there's the choice of axioms, there's the choice of language, there's the choice of symbols. So it can get very difficult to decide what is mathematics and what is not. Even if the facts are out there, other beings may comprehend it and express it and communicate it very differently from the way we do. So we still have a problem recognizing mathematics, even if it exists in other places. And what I want to talk about today is the different forms that mathematical concepts can take. Even basic ideas such as numbers 1, 2, 3, 4 can be understood in many different ways, and they have been understood even among humans in very different ways and at different times in history. So I have a history of mathematics interest, so I'll be giving you some illustrations from the history of mathematics. And this includes even such basic things as the natural numbers 0, 1, 2, 3. They, as I will show you, can be understood in different ways. And we like to think, well, if you've got numbers, you've got adding and multiplying too. And so hopefully alien mathematics includes numbers and it includes adding and multiplying. And let's look at just one example of a fact about multiplication, which is that A times B equals B times A. Now, even this simple fact has been understood in different ways at different times in human culture. And that's the main thing I'm going to talk about today. Different ways of looking at AB equals BA. Now, here is how the Greeks understood it in Euclid's time, which was about 300 BC. A and B, in this case, were viewed as lengths, and you make a rectangle from those lengths. And obviously, it makes no difference whether you turn the rectangle this way or that way. So AB is equal to BA pretty obviously, and almost by definition, if you look at multiplication as forming a rectangle. And this idea had a really powerful grip on Greek mathematics. They were very fond of it, and it has some advantages. And here's one that I like to point out to my freshman students, who very often get it wrong when they try to calculate the square of A plus B. They think it's A squared plus B squared. You will never think that if you think of this picture of multiplication, which is showing that if you've got a square with A plus B on one side, that it's made of 4 pieces. It's made of an A squared, yes, that's the square on A. It's made of a B squared, which is the square on B, but 2 other pieces, which are both AB. So you see immediately that the square of A plus B is A squared plus 2AB plus B squared from this point of view. So it's a very attractive and clear demonstration of what multiplication is. And to show you how fond the Greeks were of this idea, they even made coins with this pattern on it. This is 400 BC, even before Euclid. And I'm not an expert on ancient Greek mathematics, but a colleague of mine who was assures me that this is what the Greeks were thinking about when they made those coins. They were thinking about the square of A plus B. So there is an ancient idea. It includes the fact that AB equals BA, and it's somehow very attractive to our view of mathematics. Maybe because we have a very strong visual system. We appreciate things that are presented visually. And this concept persisted for a long time. I like to show you this quote from Newton, because this is comparatively recent and yet quite alien. It takes you a while to read what he's saying here, partly because he's using the Old English. This is the, it's not ye, it's the. and this is in which. And he's talking about two curves here intersecting. So it could be, say, a circle, which is a curve of degree 2, and a line, which is a curve of degree 1, and they would intersect in 2 points. He's saying if you have a curve of some degree and a curve of another degree, the number of points is the product. But he doesn't say product, he says rectangle of the number of. So he's talking about the product of the degree of one curve with the degree of another being the number of points of intersection. At most, it's a bound. It cannot be greater than the rectangle of the number of their dimensions. So Newton, many millennia after the Greeks, still thought of the product as a rectangle. Now here's a 19th century example. Dirichlet was one of the great number theorists of all time. He understood numbers better than almost anybody. He wrote this great book on number theory in 1863. But his starting point was also the rectangle picture of multiplication. He's not talking about lines anymore. He's talking about numbers of objects, and you've got rows and columns. And again, it's obvious from this picture that A times B equals B times A. You can think of A rows of B columns or B columns of A rows, whatever. 3 times 5 equals 5 times 3 because of a picture like this. So up until very recent times, this rectangle picture of multiplication dominated people's thinking. It seemed the best and maybe the only way to think about multiplication. For over 2,000 years, this picture persisted. So now comes a dramatic and strange event. In fact, 1860s again. This is my first alien mathematician. He's a human mathematician, of course, but he had a totally strange way of thinking about numbers and multiplication. And I'd like to explain a little bit about his background. Grassmann was a high school teacher. He wrote this textbook for his students. He was also an expert on Sanskrit. He compiled a Sanskrit dictionary. He translated some of the Sanskrit classics like the Bhagavad Gita. So he was thinking on a very different plane from most mathematicians. Whether that had anything to do with his ideas about arithmetic, I've no idea. But he was the first to realize that the most important thing about natural numbers is induction. Now, I should explain the word induction, perhaps, because for mathematicians, induction has a very specific meaning. It comes from the idea that you get numbers by a process of starting at 0 and repeatedly adding 1. So there's this recursive or repetitive process for generating numbers. And therefore, if you want to prove a fact about numbers, you can do so by first proving it's true for 0 and proving that this fact persists or propagates from each number to the next. That's the so-called method of proof by induction. You can also define functions or properties by induction by first defining them for 0 and then showing that this definition can be continued from each number to the next. Grassmann used this, to define addition and multiplication. Now this will take a little time to absorb, I think. So let me go to this side of the audience for this. Supposing you want to define what m plus n is for all values of m. So you start by defining m plus 0, which is of course m. Now supposing you know what m plus n is, how do you define it for the next number, which is m plus the successor of n? That is the successor of m plus n. So assuming this successor process, which takes you from each number to the next, you can define the addition function by going from 0 and then from each number to the next. And if you've got addition, then you can define multiplication, again, starting at 0, m times 0 is 0, and supposing you've defined m times n, and you want to define m times the successor of n, you use the addition function because the correct answer is m times n plus m. So having defined plus previously by this inductive one number to the next process, you can define multiplication by a mixture of going from one number to the next and using the function plus, which we previously defined. So there's this kind of cumulative process which is typical of mathematics. Mathematics always builds on previously obtained results. But it's not visual at all. You'd probably only get confused if you try to make a picture of that. The only picture really is this picture, the numbers going from one to the next jumping along a line. That's the only picture involved, if anything. And this was such an alien idea that it certainly didn't catch on in high schools. I think even the new math in the 1960s didn't succeed in inculcating this idea. It wasn't discovered by other mathematicians or wasn't appreciated by them for a few decades, but eventually Desargues in 1888 and Peano in 1889 picked up on the same idea. And nowadays we call this style of defining numbers in arithmetic Peano arithmetic. It doesn't quite deserve all the credit, and in fact Peano himself admitted he got the idea from Grassmann. But nevertheless, the name has stuck, and this is known as Peano arithmetic. And we've only just got started defining addition and multiplication. We're a long way from proving that A times B equals B times A. And this happens to be quite a difficult job. It turns out you've got to prove virtually everything else before you even get to this fact that A times B equals B times A. You have to prove A plus B equals B plus A. That's not quite obvious either. And things like this, associativity and properties of zero and negatives, all this stuff has to be done before you even get to this. So don't even try to think about all the details of that. Let me just show you a page from Grassmann's book. So it's item 72 in the book before he gets to AB equals BA, or alpha beta equals beta alpha. And this is his proof. He's doing some calculations here, and he's referring back to previous results, 62 and 71 and 68 and 63. So a whole lot of previous theory has to be developed before you can prove AB equals BA. So this is pretty alien, but supposing there are creatures somewhere in the universe who don't have a good visual system and they have no idea what a rectangle looks like, they may be forced to do it this way. And it gets worse. What about set theory? Now, set theory is a even more recent development in mathematics. It started around 1880. It turned out that the concept of set is a convenient language for describing all of mathematics, and that's why it's caught on pretty much today. Now, you make a set by considering some collection of objects as a sort of completed whole. Now, this includes the empty set, which has got nothing in it. That's the simplest set. And this looks kind of like a joke. And in a way it is, but it's a true joke, and it's a very tasteful joke. You can build everything out of nothing in mathematics. In particular, you can build all the numbers out of nothing. You start with the empty set and call that number 0. And your number 1 is the set whose member is 0. Its member is the empty set. So we now have two numbers, 0 and 1. So we can build the set 2 whose members are 0 and 1. We now have 3 things, so we can build the set 3 whose members are 0, 1, and 2. And so on. We can keep going from one number to the next. We have this successor function which consists of, the successor of n consists of the members of n, like successor of 2 is the numbers up to 2, together with the number n itself, which in this case would be putting in 3. So this strange process, starting with nothing and then building sets, allows you to produce the series of natural numbers, and also the successor function arises naturally. So set theory, this is von Neumann's idea. Set theory includes the numbers. So we can now plug this into Grassmann's idea. We've got the successor function, so we can define addition and multiplication. And you can, in fact, do all of arithmetic inside this so-called finite set theory. Now, this was done in the 1930s. So this is coming towards fairly recent times, that it was discovered that number theory has this totally different incarnation, where the concept of set is the basic concept. And I should tell you a few other little things about set theory. It's not obvious. We've got a successor function. I've explained that. But it's not obvious what addition and multiplication are, other than Grassmann's definitions. And set theory, in fact, looks very different. It has these four principles for constructing sets. If you've got two objects, you can collect them into the set whose members are those two objects. We were doing that on the previous slide. The union. Now, probably some of you have met the idea of the union of two sets. You've got a set here and a set here, and you just collect them all together. Well, you could have many, many different sets and you collect them all together. That's the union process. So you form the set of members of members. The power set, as the name suggests, this is a very powerful operation. You collect all the subsets of a set. Now, if you're starting with an infinite set, that's a lot of sets. But if you were in the finite sets, which was all we need for doing arithmetic, you could list all the subsets. And so it's doable. Now, replacement is if you've got a set and some function, you can collect the set of values of the function. That makes a new set. So these are the basic principles. They don't look at all like arithmetic, but surprisingly, if I can go back for a moment, you get exactly arithmetic by restricting to finite sets. This setup gives you arithmetic. So this is getting even more alien. We're not talking about addition and multiplication anymore. We're talking about things like pairing and union and power set. And see, maybe aliens like to think this way too. Maybe they like to think in terms of sets. And they would prefer these operations to addition and multiplication. In which case, it would be very advanced mathematics for them to prove that AB equals BA. This could be the case. But as I said, you can get this set whose member is X by this kind of sly trick of pairing X with itself. The set whose members are X, and X is the same as the set whose member is X. And then you can get the successor function with this union operation. So out of these set building operations, we can build the successor function, and therefore addition and multiplication. But it's a very roundabout process, I must admit. But it could be the way that other beings do it. And we certainly are very attached to the idea of set theory nowadays, because it's only one step beyond arithmetic. If you add this so-called axiom of infinity, you can get so-called Zermelo-Fraenkel set theory, which is, in a sense, a theory of everything. All of mathematics can be done if you start with the arithmetic, as I previously described it, add this axiom that says there's an infinite set, and in more detail, it says that for any member of this set, the successor is also a member. So that's sort of saying the natural numbers exist. You pick an object, and then there's a successor of that, and so on, and so on, and so on, indefinitely. So you're claiming in this axiom there's an infinite set, and this axiom alone, added to arithmetic, creates everything. It suddenly explodes. You get real numbers and functions and complex numbers and spaces and everything that mathematics wants to talk about is available once you've added this axiom. So I think if aliens are any good at mathematics, they ought to hit on this axiom. But maybe they don't believe in infinity. A lot of people don't, I must admit. So maybe humans are strange in believing in infinity. But this is such a powerful axiom that it's hard not to believe in it. So that's one direction you can go in. If you analyze the concept of number very closely, it seems to drive you towards this concept of set. I'm not saying that this is the only way, and in fact I want to talk now about something entirely different and come back to geometry. Now the geometry I mentioned before, Euclid's geometry, is not merely a visual thing. I sort of suggested it was perhaps, but it's not only visual. It's kind of tactile too. It sort of assumes that there are rigid objects, and because to measure things, which of course you do in geometry, that's what the word means. Geometry means measuring the earth. To measure things you need rigid objects, and in fact this survives in our words for measure of length, like the foot, for instance. We use that as a measure of length because everybody's foot stays the same length once they're finished growing at any rate, because it's got bones in it, and bones are rigid. And your arm has got bones, and your arm is rigid. So I believe that the yard, the original yard, was the distance from Henry VIII's nose to the tip of his fingers. So our concept of geometry is very dependent on the kind of bodies we have, which have these rigid parts called bones. But there is another kind of geometry, which really is the visual part of geometry, and we call this today projective geometry. And it's about how things look rather than how things are measured. Now, I can give you an example of a projective effect if you look at the ceiling here. Now, we all know very well that this ceiling is made of square tiles. But if you look to the side, or look to the front, you will see that those tiles do not look square at all, and they don't look equal either. They appear to get smaller, and the angles are not exactly right angles. So our vision is somehow extracting information about squares from a picture that is not consisting of squares. This is projective geometry. And this arose when artists wanted to make pictures of things like tiled ceilings and tiled floors, and they wanted to depict them accurately. And I've got here an example of the starting point of such a problem in drawing. Supposing I set up this picture with a tile. It could be one of these ceiling tiles. It's got parallel sides, and therefore those sides appear to meet on the horizon. This is the key secret of projective geometry, to introduce this horizon line where parallel lines meet. And once you've set up the basic tile like this, you can produce the other tiles in the floor by this trick. You draw the diagonal of the first tile, which will also go to the horizon. Now, the diagonal of the second tile is going to be parallel to this. Therefore, it will meet at the same point on the horizon. I'll draw that one too. So now I've got, you notice, the corner of the second tile. So I can complete the second tile by drawing a line there, which I will. And then I've got the starting point of the diagonal for the third tile, which I can draw. And then I complete the third tile, and a fourth diagonal, a fourth tile, and so on. I can keep going and get this accurate picture of a tile floor or a tiled ceiling, such as we see in this room. So this is a kind of non-trivial problem. I think you will agree. It wasn't solved for a long time. And In fact, this version of the problem probably wasn't clear until the 19th century. When artists solved this problem, they cheated a little bit by making some measurements. But this requires no measurement at all. It's all about straight lines. And straight lines, I guess, ought to be part of anybody's geometry because light travels in straight lines. So if you're aware of light rays, I think you're going to be aware of straight lines. And so you have the potential to develop projective geometry. Now, in this picture, you sort of have numbers as well because the tiles look equal, so it's like we're finding numbers and spacing them along the line. Here we are, 0, 1, 2, 3. So this, in a way, is also a new version of the number sequence, which I can continue further and further. So maybe we can also construct sums and products and come back to AB equals BA through this route. And that's what I intend to do. At first, let's reflect on what we were doing here. We were drawing lines, but we only draw a line when we have 2 points already available. So the next line I'm going to draw is going to go through this point and this point. If I have 2 points, I can draw a line through them. And when 2 lines meet, I get a new point. So that gives me a new place to start drawing a line. So here are 3 things that we are assuming when we make those pictures. First, we assume that there are 4 points, no 3 in a line. That's the tile that we start with. Through any 2 points, there's a line. Any 2 lines meet in a point. That includes parallel lines because we've included the horizon where parallel lines meet. So there's a little bit of magic in this, but it's magic that is sort of dictated by our vision of parallel lines converging towards a point. However, these 3 fairly obvious facts don't account for everything that happens in the drawing. Certain coincidences occur where you have 3 points that seemingly by accident lie in the same line. Now I'll show you one of those in the picture again. Am I there yet? I don't think so. Have a look at that for a moment. See if you can see 3 points where lines cross each other. 3 points that are on the same line. Anybody see them? Okay, you're right, it's there. Now, that seems like a coincidence. Of course, you're going to need a lot of coincidences like this for the floor to look right, but it doesn't follow from those previous principles that I laid out. So something extra is needed to explain these extra characteristics of drawings of the tile floor. And I want to tell you about some of these. They're known as theorems of geometry because they were discovered a long time before this projective geometry was invented. One is called the Pappus theorem. There's the Desargues theorem and the little Desargues theorem. I'll show you some of these in a moment. But any one of these can be used to generate a lot of facts, in particular all the facts that you need to explain in the tile floor. So they're sort of a gateway to a lot more facts. So these, like the axiom of infinity maybe, are something that smart alien mathematicians ought to notice as being very fruitful. Pappus is the most fruitful because it implies all the others. And one of the fruits that we'll see is AB equals BA. So first of all, let me tell you what the theorem is. I'm using the word hexagon here in perhaps an unfamiliar way. I'm talking about this 6-sided figure made of red, blue, and green lines. And the vertices of the hexagon lie alternatively on 2 lines. So the hexagon gets kind of crumpled up, but it's still got 6 sides, so you could call that a hexagon. Now the property of this is, if you extend the like-coloured sides, which I'm calling opposite sides, they'll meet somewhere, and you'll probably notice something interesting about the points where they meet. lay lie on a line. And so this is Pappus' theorem, which is that however you draw this hexagon, the extensions of the sides will meet on a line. An amazing kind of coincidence. That was around 300 AD that Pappus proved that. And he proved it not in the context of perspective drawing or anything. It was a theorem of ordinary geometry for him, and he used lengths to prove it. But we now see this theorem in a somewhat different way. It's a way of, it enables us to extract arithmetic from geometry. And the fellow who first thought of doing this was Christian von Staudt, who wrote a book on projective geometry in 1847. And he proposed this idea of using projection to define addition and multiplication. He didn't quite complete this project. It was later completed by Hilbert. But I can show you the gist of it. Let me come over to this side of the audience for a change. Supposing I want to define addition of A and B. I'll choose them to be points on a line, and I'll choose another point to be 0. Now, I'm going to cheat a little bit at first and pretend I have a compass that I can spread out so as to stretch from 0 to A. And if I can do that, then I can slide the compass along and put one end at B, and that presumably will go to B plus A. So let me show you that. There I've shifted the original, so the original goes faint, I'm afraid, which might be a little hard to see. And here's the new position of the compass going from B to A plus B. Now all I've needed here are parallel lines. And if you think back to previous pictures, parallel lines are simply lines that meet on the horizon. So you don't have to think of them as literally parallel. Parallels can be interpreted as just lines that meet on some line that I choose and call the horizon. So this can be done without really needing parallels. So that's how you would define addition. Well, that's adding A to B, but you could also add B to A, and it's not necessarily the same thing. Here's how you would define add B to A. First, stretch your compass out from 0 to B, and then slide it along, and put one end on A, and the other end should be on B plus A or A plus B. I've forgotten what I call them now. B plus A, okay. It's a different construction, so it won't necessarily be the same place. In fact, there'll be a coincidence if it is. But that coincidence happens, because if you can see the faint lines here, what I have got is the Pappus setup of 6 points alternatively on 2 lines. And the coincidence of Pappus says that those 2 ends must end at the same place. So that's A plus B equals B plus A. There's a similar thing for A times B equals B times A. So let me tell you a little bit about magnification or multiplication. To multiply numbers, we have to know not only the numbers A and B, but also the number 1, because the number 1 is important in multiplication. It's the number that does nothing. And if you want to multiply by A, first of all, you make this kind of picture of A by stretching your compass from 1 to A, and then you slide those 2 sides parallel to themselves. There they go. And you see it's magnified because of the fact that the 2 lines diverge. And we have magnification by a factor of B, so we should have B times A or A times B rather. So that's magnifying by A. And again, it uses only parallel lines, which don't really have to be parallel, they just have to be lines that meet on the horizon. So this is a purely projective construction of multiplication. And just as I can magnify by A by stretching from 1 to A, I can magnify by B by stretching from 1 to B and then sliding them parallel to themselves. So this is multiplication by B. But again, why should that end up in the same place? It will be a coincidence if it does, but it is. It's the Pappus coincidence. Again, let me draw your attention to the faint lines here. With the others, they make the 6 lines of the Pappus hexagon. So the Pappus theorem comes to our rescue if we want to know whether b times a equals a times b. Pappus theorem says that they are equal because this is exactly the Pappus setup. So there is another totally alien way of understanding why a times b equals b times a. But if you're an alien who does geometry mainly by vision, like if you're some kind of jellyfish and you don't have bones to create rigid objects and measure things, this might be the way you think of geometry. This may be the most natural kind of geometry for you. And so we should take this seriously as another option for understanding why BA equals AB. Now, as I said, Pappus is very fruitful and actually gives us a lot more than that. And I think it outclasses the previous conception of multiplication, which gave us a little bit of algebra, but not a lot. See, the trouble with the concept of the Greek multiplication, where you just put your 2 lines together and make a rectangle, that multiplies 2 things. To multiply 3 things, you've got to go in the 3rd direction, and you've already used up the 3 dimensions of space. So for the Greeks really did not believe that it made sense to multiply 4 things together, because they could not imagine 4 directions perpendicular to each other. So that was a serious limitation to algebra from the Greek point of view. The projective definition of multiplication that I gave you doesn't have that limitation. You can keep multiplying things because you keep getting another point on the line. When you multiply 2 points on the line, you get another point on the line. So you can keep multiplying as long as you like. And you not only find a plus b equals b plus a and a times b equals b times a, but a lot of other things too. All of those things that I listed before, plus inverses of multiplication, you get the so-called field axioms. There are 9 of them. A plus b equals b plus a times b equals b times a, and then there's the associative and distributive, if you know these terms. They're altogether 9 axioms which are constantly used throughout mathematics. They're one of the basic structures of algebra, the field axioms. And it's sort of the basis of high school algebra too. High school algebra constantly uses the field axioms even though it may not always explicitly describe them. So if aliens want to communicate the concept of a field to us, the most concise way to do it would be to send a picture of the Pappus configuration, because that implies it all. But you certainly have to be smart to notice that. And so this is what worries me about what alien mathematics could be like. They could be sending us something that we don't understand at all because the mathematical structure is hidden from our point of view. It may be obvious to an alien that you have addition and multiplication here that satisfy these axioms. But it's certainly not obvious to us, and it took 2,000 years of mathematical development before this was known. Now also, supposing you wanted to communicate just this one of the 9 axioms, how might you do that? Somehow we've got to distinguish it from all the others. Now there is a theorem that does that too, and it's another projective theorem called the Desargues theorem. It was on my list earlier. And it says, if you have 2 triangles in perspective, meaning that there is a viewpoint from which one lies exactly on top of the other. So there's a point where these vertices line up and these line up and those line up. Then, again, you might try extending the sides, and you'll notice that again, the intersections lie on a line. Another amazing coincidence. This is Desargues' theorem. Now, with the help of this theorem, you can also prove facts about addition and multiplication, but not quite as much. In fact, you can prove everything among the field axioms except AB equals BA. So AB equals BA is what's implied by the Pappus, but not by this. So that's a very tortuous way of describing the fact that AB equals BA. It's described by two pictures, the Pappus picture and this one. So I've taken you on a pretty wild ride here, and if it seems confusing, that's, I don't mind that, because I think that illustrates the problem of interpreting what alien math might be. When I prepared this talk, a few months ago, and I kept fiddling with it. And rather belatedly, I thought I would look up some literature on the subject. And I came up with two rather interesting papers that I'd like to recommend to you. And I'll say a little bit about both of these. They're both from around the year 2000. This one is online, freely available. It's probably published in a book somewhere too. This one is in the American Mathematical Monthly. It's online if you have access to JSTOR. And they're quite different in tone. I prefer the first one myself, but I'll briefly describe what they're about. The David Ruel paper, it's this fictitious conversation between an earthly mathematician and a visitor from outer space. And the alien mathematician is very tactful and really only wants to talk about the earthly mathematics because she feels she can't convey alien mathematics to this guy. But it sort of focuses on the human peculiarities of mathematics, how the human brain favors some parts of mathematics and makes other parts difficult. And he points out, for instance, we're fairly weak on calculation, mental calculation. We're rather weak on memory. We can only remember a small number of random objects, like a telephone number, for instance, is about the limit of what we can remember. But we're very strong on visualization. We seem to have a very good visual system, so we can comprehend quite complicated pictures and two-dimensional, three-dimensional. But he also says not all mathematicians are like this. And I know of examples myself, but he mentions another very distinguished mathematician who seemed to have no ability to visualize things. I had a roommate in graduate school who told me he could not even visualize a circle. I find that hard to believe, but so somehow human mathematics compensates for lack of visual ability, and people can do geometry without being able to see it, yet it's a great help to most of us. And that's sort of the focus of Ruel's article. It's on the limitations of human mathematics. And by knowing the limitations of human mathematics, I think you get a better idea of what other options may exist. Now, the Hamming article, it's kind of, the article is written by a cranky old man, basically. Hamming wrote this towards the end of his life. And he starts off by considering what mathematics aliens may have, and he fairly casually assumes that they'll do much the same as us, that they'll have numbers and they'll have geometry. But then he goes on to rubbish a lot of human mathematics. It turns out there's a lot of human mathematics that he doesn't believe in. He doesn't believe in infinity. He doesn't believe in anything that's not computable. So it's more a denigration of human mathematics than a projection of what alien mathematics might be like. But it's still very interesting and very thought-provoking. So I'd like to recommend those things to you if you want to study this further. And I'll also be happy to take any questions that you may have. Yes?
Can you use geometry to demonstrate multiplying by a negative number?
Yes. The line that I drew had 0 at one end and then it went to A, B, and so forth. But you can extend the line in the opposite direction, and negative numbers are very much included in that setup.
If you have a question, just put up your hand.
Can anyone hear me?
No, you need to report.
Hello. Oh, okay. You know, Grossman, I noticed when you mentioned he studied the Vedic scripture.
Yeah.
My son been practicing Vedic math for the last year now, and he's 10 years old, and he's able to do our traditional Western concept of mathematics up to calculus. But the thing is this, is I realized that the Vedic mathematics is a progressive because they don't try to prove the in-step, they're just showing you the progression, and thus a lot of it is intuitive jump. And I think the induction method is based on that whole concept because a lot of Vedic mathematics is mental mathematics. You do not even have to use the board.
Oh, that's very
So
interesting.
he could do a lot of multiplication. Now, of course, we call it a trick. Whether it's a gimmick tricks or whether it is an intuitive nature in us to able to perform at this level, it's incredible. And it's, to me, it's like alien mathematics because if we taught this to our kid today, I think our kid fully understand our basic mathematics a lot easier than so-called the new math.
Yeah, that's interesting. I don't know whether Grossman was aware of Indian mathematics, but since he did study in Indian literature, he may have been.
A lot of Indian literature is scientific literature with mathematics.
Yeah. So it could be that was an influence.
An alien introduced to humanity mathematics before we even knew what mathematics is, and we just keep discovering it.
Thank you.
Have you considered a mathematics that could be based on sound, like musical scale, for example, as one question?
Just as vision has influenced mathematics, music has to some extent. I wouldn't say to the same extent, but the whole idea of what it's called, harmonic analysis. There's a seepage of musical terms into mathematics. Harmonic series, harmonic analysis, the theory of vibrations, for instance, has been an influence of music on mathematics, but mainly at a higher level. Actually, it's hard to say synthesize numbers from ideas in music, though it might be possible.
And my other question is, have you considered a mathematics based on fractal geometry? Can you have you considered a mathematics based on fractal geometry? Because that's what's in nature here, at least.
Yes. Again, I think fractals are a fundamental part of mathematics. But again, it's difficult to see them at the lowest levels generating simple concepts. It's more a higher level concept. There are many, many strange and alien concepts of mathematics. I was trying to concentrate on lower level ones today, but there are certainly many others.
So maybe going back to Russell, where mathematics is merely applied logic, one not going that far, but saying, examining the notion of proof and deduction, would you, I mean, that might seem to be a more fundamental test of correspondence or lack of correspondence. Do you have any notions of what
Yeah, I think
deduction and proof might be?
The Russell and Frege idea of building mathematics out of logic is similar to, they're not quite the same as the set theory construction using the empty set and so forth. There's a kind of parallel between them at any rate. And yeah, the Russell concept of the number 1 and 2 and so forth is rather more complicated because he says the number 2 is the class of all sets which have, well, you don't want to say 2 because that's circular, but you know what I mean. It's somewhat less elementary than the von Neumann definition, but they're in the same kind of ballpark, I think. Yeah.
Oh, yeah. It seems like you started off by immediately throwing yourself in the camp of the Platonists.
Yes.
And it seems like right away where a real difference in mathematics could happen if we put ourselves in the intuitionist camp and thought that, now I myself am in the camp of the Platonists and the empiricists, so I'm not going to argue with that. But it seems like you've done you've come up with some great examples that show how a simple concept in our scalar mathematics can have several different representations.
Yes.
But I think you might say a word for the people here who don't do mathematics about how all our mathematics under the Platonist idea is reducible as isomorphic to natural numbers, real numbers, complex numbers, Hamiltonians. And it seems like really what you've said is that they will have the same mathematics but derive it differently.
Well, that's my guess.
And
yes.
express it differently.
Yes. Yeah.
I was going to offer one comment and then I'll...
Yeah. Do you have... See, it's very hard to give an example except what we already know. But go ahead.
A lot of what we kind of spend time thinking about here are the constraints of the universe, and we assume that, for instance, most beings are going to grow up around planets and probably in a flat space-time, where they're going to have some of the projective geometry we have, some that we don't. An interesting thing to think about might be the situations where commutators, where commutative property isn't.
Yes. Good point. I didn't talk about the possibility of A being unequal to BA, and of course that's a very important possibility too. It's not true of natural numbers, but quaternions, as you mentioned,
But
it is.
Even so, if somebody grew up near the Schwarzschild radius of a strong gravitational object and didn't have commutators that were naturally zero, it seems that they'd be able to reduce it and I think that we should be able to, if they have to encode it and send it via light, they should be able to reduce their geometry or their mathematics to a standard form. It bears some thinking about.
Yes.
Whether it's the same mathematics under the same form or actually a really different mathematics.
Yeah, that's a definite possibility, but it's so difficult for us to grasp, and it's seemingly humans will have to discover this different mathematics before we can recognize it in other beings. That would be my guess. Anyway.
Yeah, you spent a lot of time talking about the low-level mathematics for the purpose of this, and I'm wondering, it got me thinking about like higher-level stuff like calculus. I could see, for example, species evolving in a gas giant, maybe developing calculus because they need to solve problems before Euclidean geometry, because that might not be intuitive. And I was wondering if you thought that, irrespective of whether you do number theory or set theory, whatever, when you get to the higher levels, like calculus and real analysis and things like that, do you think that they would wind up in the same place, built on different Lego bricks, as it were, or whether you think you could wind up in radically different higher places?
I suspect you could wind up in a radically different place because we, human mathematicians, haven't considered the different possibilities very much yet. We've hit on a few things like number theory, Euclidean geometry, calculus, and we've sort of concentrated on finding an environment that will hold those nicely, and set theory is one such environment. There could be other things that we simply haven't considered and which will require an entirely new framework. It's a possibility, but again, I think we have to think of that ourselves first before we can recognize it in other beings.
You mentioned the Pappus theorem and the Desargues theorem. What is the little Desargues theorem?
Oh, the little Desargues theorem, it's a special case where the point of perspective lies on the horizon.
Is it really credible to you that an alien brilliant enough to understand all the theories you've gone into today would not have noticed and attached importance to the fact that A objects taken in B groups and B objects taken in A groups add up to the same number of objects, and what that means?
No, I think that I can't imagine anybody not noticing that if they were capable of doing these other things. But yeah, I think we've got to be open to the possibility that they might think of something else first. But I agree, it's very difficult to imagine. But that's the whole problem about things. Difficulty of imagining things is the whole problem. Yes?
So I'm trying to wrap you're using tools which are spanning 3 millennia here.
Yes.
Zero, algebra, commutativity, and the like. And so I'm wondering, is there going to be a remote extraterrestrial equivalent of a Bourbaki? Because we face this problem. I mean, I know about the mathematicians you talk about also who cannot visualize things, and I'm a much more visual thinker myself. And I think the Bourbaki did a lot, unfortunately, to
discourage visual.
Yeah, to destroy a lot. You know, the whole death to triangles thing.
Yeah. I think we should use all tools available, and that means collectively. If some people are not good at visualization, they should ask for help from others who are. But by the same token, it is interesting that you can find a way around visualization and do things differently. And that I think gives us some insight into the different ways that mathematics might be done extraterrestrially.
John, are there any? Obviously, it's difficult to know without us having met ET yet. But are there any gaps in human knowledge that you feel would be best filled by, or could be filled by mathematics?
Now, I'm glad you brought that up, because that's reminded me of something. The Indian mathematician Ramanujan discovered a lot of amazing theorems that he did not know how to prove. He just somehow had visions of these things. And it's taken a lot of work by other mathematicians to find proofs which are maybe nothing like what was in his head. And maybe one day we'll find an alien who can tell us what Ramanujan was really doing.
On the projective math here, and one thing really shook me up was the ability for it to go into the higher axis dimension, where traditionally we are seeing either in the 2 or 3, but this one is at infinitively. And when and this is an assumption, I'm asking you this question. When an alien assume that he is able to visit, or they are able to visit us, that their mathematics is higher than our, in other words, their conceptual understanding of the fundamental relation between nature and itself is much, much more cohesive and clear than our. Thus, in turn, if we continue to progress in our humanoid mathematics, we are able to achieve the level of higher dimension without visualization, because it seems like the more dimensional axis you put on, it's become more complex. And another thing I noticed that was really interesting is at the horizon, it seemed everything to meet at one point. And thus, would that explain a lot of our so-called gravitational curvature in space?
I'm not expert enough to answer that question. As for the higher dimensions, I have heard it claimed that some mathematicians did have a good understanding of the four-dimensional geometry. And others have said, I think Poincaré might have been one of them, that you could perhaps train somebody from childhood to be able to think in 4 dimensions. But it's probably a cruel experiment that you wouldn't be allowed to try. So yeah, there may be other ways to access 4 or higher dimensions.
John, some mathematicians are obviously using more of their mathematical faculties than most of us.
Mm-hmm.
Euler springs to mind.
Yes. Yeah.
Do you think aliens could teach us how to all become Eulers, or is this something?
Yes. Yeah. Maybe there are ways of learning that we've overlooked and that would make it a lot easier. I would love to know them.
Well, if there's no further questions, I'd encourage you to come up and ask your questions directly with John. And John, we have a special commemorative mug. Please come here and speak with
Well, thank you again very much.